nanoHUB.org.
Online simulation and more for nanotechnology.
Hi, my name is Arvind Raman. I'm a professor of mechanical engineering at Purdue.
And I'm Ron Reifenberger, professor of physics at Purdue. Together we've developed this web-based 10-week course called Fundamentals of Atomic Force Microscopy. And in the next 10 minutes, we're going to provide you with a very brief scientific overview that sort of summarizes the material that's covered in this course. This is a new initiative at Purdue University. It's offered under the nanoHUB-U initiative. And the course has really been developed because of some very positive feedback we've obtained on a course that we gave here at Purdue back in 2009 and 2010 that covered the fundamental aspects of atomic force microscopy. So as you probably know, the AFM contains many different components. And to properly use this instrument really requires you to have some understanding of many different areas of science and engineering. In this course, we intend to emphasize the link between nanotechnology and AFM. You need a broad background in science and engineering from many different disciplines in order to understand how this instrument works, in order to understand what the instrument measures. So what we do here is we summarize the different areas of research that you probably need to have some understanding of in order to fully appreciate how an AFM works. You truly have to be multidisciplinary, and oftentimes you have to be an expert in more than one area in order to properly appreciate what this instrument can do. Now, if you lack the resources or if you lack the time required to understand these different areas, then this course is for you. We intend to provide the background material. We'll review the necessary mathematics. We'll cover the derivation of important equations from all these different areas of science and engineering. What will the course cover? Well, the course is split into two parts. Part one of the course will focus on the background and fundamental aspects of AFM. It'll focus largely on the static cantilever. We're going to talk about non-contact tip-surface interactions. We're going to show you how the equations that govern these interactions are derived. We're going to talk about the tip in contact with the surface. We're also going to broadly talk about the AFM as an instrument. We'll discuss force spectroscopy and contact mode scans. And then lastly, interleaved between these 4 weeks of lectures, we'll discuss computer simulations of AFM experiments, focusing largely on the static cantilever using this tool VEDA that Arvind and his group has developed here at Purdue.
And in part two of the class, we're going to focus on dynamic atomic force microscopy methods, which have been chosen to be the focus of the second part because dynamic AFM methods tend to measure and sense the tip-sample interaction forces in a very different way. What you see at the back on the board here is an example of what dynamic AFM does. And what we have in dynamic atomic force microscopy is we have a resonating cantilever, and we tend to sense and measure forces between a few atoms on the tip and a few atoms on the surface by means of how those forces change the oscillations of this probe. And so in order to understand dynamic atomic force microscopy, we really need to have a very good understanding of the coupled model of the oscillating cantilever and interaction forces, and really understanding how one affects the other going both ways. So in this class, what we're going to be doing in part two is starting with the point mass oscillator model, which is basically the simplest model that allows us to explain a very large amount of the physics of dynamic AFM methods. And we will go through analytical theory of dynamic AFM, which includes things like phase contrast imaging, peak forces, average forces. How do all these things relate to the local properties of the sample and to what one observes in the atomic force microscope? We will go through a week on trying to understand how Veda simulations can be used to understand how artifacts can come up in dynamic AFM methods, to understand what the link is between tip sample interaction properties and phase contrast or changes in the amplitude and so on. We will, of course, also be looking at different ways of doing dynamic atomic force microscopy, which include, for example, tapping mode or amplitude modulation AFM, FM AFM, and phase modulation AFM. So we'll be covering those aspects as well, and we'll also be dealing with how these observables in dynamic atomic force microscopy can actually be used to generate quantitative estimates of local properties through a process called force reconstruction. And towards the end of the class, we will move on to speaking about electrostatic force microscopy. We'll touch on magnetic force microscopy, and importantly, we will actually look at aspects of dynamic AFM in liquids when applying it to biological samples, which is a pretty different area of application of dynamic AFM methods. And understanding dynamic AFM in the context of liquid environments is quite challenging and difficult, and will be covered in some depth in this class. To fully benefit from the material that we're going to cover in the class, we recommend certain prerequisites. And those prerequisites are going to include certain classes you might take at a freshman or sophomore level, for example, differential integral calculus, differential ordinary and partial differential equations, a standard introductory 2-semester class in physics would be a very relevant background for this class. Beyond these freshman or sophomore level classes, we do believe that if you have exposure to other undergraduate level mechanics classes, such as statics, dynamics, mechanics and materials, or a class on electromagnetism, or a class on quantum mechanics with particular emphasis on atomic structure, all these would help you and understand parts of the class better and faster if you do have this background. Now, one of the important features, as was mentioned earlier, of the class is going to be that we are covering a lot of material, and we're going to provide all the background to understand the equations and the theory that arises. In doing so, one of the things we've had to do, one of the challenges we've had to deal with is how to have a unified treatment across all these different areas of physics and mechanics and engineering and science put together. And this is a particular highlight and feature of this class, and we're going to deal with common notation, streamline terminology, and make it all consistent through both parts of the class. Another very important piece of what distinguishes this class is the use of simulations using Veda on the cyber infrastructure of the nanoHUB. And what this allows you to do is actually perform numerical experiments to really understand and make sense of the theory and the physical principles being discussed in the class. And it really is like doing experiments, except it's on a computer, and it's done through this freely available software.
So to summarize, the purpose of this 2-part course is to provide a comprehensive and unified overview of AFM. We'd like you to understand the important equations encountered in AFM, and we'd like you to learn how to derive and apply them correctly. We'd also like you to be able to perform realistic numerical simulations using the Veda software. And lastly, we'd hope that you would broadly recognize the advantages and limitations of AFM as you progress through your research. It's a fair question how you might benefit from this course. And there are three classes of three categories that you might fall in. And if you do fall in one of these 3 categories, we think this course will be of use to you. First and foremost, if you're a beginning graduate student and your thesis advisor has asked you to do some AFM experiments, you don't have the time, or perhaps the background required to understand all the aspects of AFM to carry out this research. If you take this class, you'll receive the information necessary to more effectively perform your research. Secondly, you might be a continuing education professional. You might be involved with AFM in your workplace, and you need to improve your understanding of AFM. If you take this class, you will improve that understanding, and your work performance should also improve because you have a better understanding of how an AFM works. And then lastly, there's a growing trend to use AFM in industry. The AFM instrument is no longer an academic instrument. It's no longer confined to academia. It's being used in a variety of different ways to solve real industrial problems. So if you're curious about these commercial industrial applications and you take this course, you're going to receive the background necessary to understand how AFM might be used for your particular application. So briefly, to summarize, if you take this course, you will receive an in-depth appreciation of AFM techniques, and you will better understand how AFM can be used for your particular applications. Space is limited in this course, so register now at the link given below, and we hope to see you online when this course begins.
Thank you for your interest.